Det norske vitenskapsakademiet kunngjorde i mars at Abel-prisvinneren for 2007 matematikeren Srinivasa Varadhan fra USA. Prisen, som også kalles Nobelprisen i matematikk, på 6 millioner norske kroner og deles ut hvert år for fremragende vitenskapelig arbeid i matematikk. 22. mai i år overrakte kong Harald prisen til Srinivasa Varadhan under en høytidelig seremoni i universitetets aula. I forbindelse med prisoverrekkelsen i Oslo møtte professorene Martin Raussen og Skau prisvinneren til en samtale.
Professor Varadhan, first of all I would like to congratulate you for having been awarded the Abel Prize this year. In fact, Skau and we have had the pleasure to participate in interviews with all Abel Prize recipients so far, and we are just starting with the 5th interview in this series now. I would also like to extend my congratulations to the field of probability and statistics, since you are the first recipients from this area. Probability and statistics is an area that most people in our audience, I guess, have some acquaintance with from their mathematical education at school. But only few of these people will have dealt with the problems and the results that you have obtained through your mathematical career. Incidentally, last year at the International Congress of Mathematicians in Madrid, there were fields medals given to experts in probability and statistics as well, but this was the first time that occurred. Maybe I should just tell to our audience that the fields medals are given to young mathematicians under the age of 40 at every International Congress of Mathematicians every 4th year. This is a very prestigious prize as well. But as I said, last year that was the first time it was given to somebody in probability and statistics. So now my question is, how come that it took so long time until probability and statistics was recognized at such a high profile with International Congress of Mathematicians last year and the Abel Prize that year? And is it a pure coincidence that it happened 2 years in a row? And maybe some comments also on the relations, the ongoing relations between probability and statistics on the one hand and the rest of mathematics on the other side, please.
I think one of the things about probability theory is that it became a branch of mathematics very recently, only in the 1930s after Kolmogorov wrote his book. Until then, it was not really considered as a proper branch of mathematics. So in that sense, it has taken some time for the mathematical community to feel comfortable with probability the way they are comfortable with number theory or geometry or algebra, for instance. That's one of the reasons of perhaps why it took a lot of time. And in recent years, probability has been used in many areas. Mathematical finance, for example, uses a lot of probability these days. So probability has had a lot of exposure and publicity. And the connections with other branches of mathematics has come up. The most recent example with conformal mapping and so on, for which the Fields Medal was given last year. So these connections have brought probability to the attention of the mathematics community, and I think the Fields Medal, the Abel's Medal is a reflection of that.
My next questions will be about your career. You were born in Chennai, in India, and Chennai is the capital of Tamil Nadu, if I'm correct, on the southeast coast of India. You were born there in 1940 and went to school there, and after that to Presidency College at Madras University. I would like to ask a bit about these formative years. First of all, what arose your mathematical interests? I know your father was a mathematics teacher. Did he have an influence on your choice? Were there other people involved? Were there specific problems that arose your interest?
My father was, in fact, a teacher of science in general, not so much mathematics. In my school days, early school days, I guess I was good in mathematics. In the sense that I could, as an elementary school, being good at mathematics meant you could add, subtract, and multiply without making mistakes. But anyway, I had no difficulty with mathematics. And then it's only when I went to high school that I had an excellent mathematics teacher who would ask some of his better students to come to his house during weekends, Saturday or Sunday, and give them extra problems to work on. And so we thought of these problems as just games, intellectual games that we play, and so there was no pressure to sort of do it like doing something for an exam or something of that sort. It was more for enjoyment. And that somehow gave me the idea that mathematics is something that one can enjoy doing, like playing chess or solving puzzles, And that attitude made mathematics a much more friendly object than something to be afraid of. And I think that played a role in why I got interested in mathematics. And, after that I went to college, 5 years of college education, and had excellent teachers throughout. And by the time I graduated with my master's degree in statistics, I've had 3 years of solid grounding in pure mathematics, and the same amount of time devoted to probability and statistics. And these were excellent teachers, and so my background was strong when I graduated from college.
Mm-hmm. Was there a specific reason that you graduated in statistics rather than other branches of mathematics?
The options are, at that time was either to go into mathematics or statistics. There was not that much difference between the two. If you went into mathematics, you studied pure and applied mathematics. If you went to statistics, you studied pure mathematics and statistics. So you replaced applied mathematics with statistics. That is the only difference between the two programs. I think looking back, the part of the reason for going into statistics rather than mathematics, there was a perception that if you went into statistics, your job opportunities were better. You could be employed in the industry and so on. Whereas if you went into mathematics, then you ended up as a school teacher perhaps. And so there was that perception. I don't know how real it is, because one could always switch. But so the people were more attracted towards physics, chemistry, and statistics rather than mathematics.
Okay. With your degree in statistics, it seems natural that you would continue at the Indian Statistical Institute at Kolkata. And there you found yourself quite quickly in a group of students that, seemingly independent of their teachers, started to study problems of a purely fundamental mathematical character. And then you applied these new methods to problems in statistics, which then gave tremendous results that other probability theorists all around the world had been trying to establish before you. In particular, you established new limit theorems for stochastic problems in higher dimensional spaces. Can you tell us a bit about this story, whom you collaborated with, and how this all developed?
When I went to Statistical Institute as a research scholar, the Indian system at that time was very much like the British system, in the sense that you become, if you go to study for your doctorate degree, there are no courses offered. You are just asked to do research, produce a thesis, and you can ask your advisor questions and he'll answer you, but there was no formal guidance as it's in the United States, for example. So when I went there, I had the ideas that since I was going to look for a job in industry, I looked around and I was told that I should work on statistical quality control as an entree to industry. So I spent close to 6 or 8 months studying statistical quality controls. It was like studying history. It left me totally unsatisfied. And then I met Varadhan and Parthasarathy and Rangarao, who were doing work in probability from a totally mathematical point of view. And they convinced me that I was not spending my time usefully, and I better learn some mathematics if I wanted to do anything at all. So I got slowly interested in it, and I think the second year I was there, we said, okay, let's work on a problem, and so we picked up a problem on something to do with probability distributions and groups. And so that got us started. We learned whatever tools we needed in order to solve the problem, and eventually solved the problem and also learned the tools that were needed for it. It was a lot of fun because we were 3 of us, constantly exchange ideas. Started at 7 o'clock in the morning. We were all bachelors living in the same dormitory. So the work day consisted of 7 a.m. till 9 p.m. and we just, it was a terrific time to learn. And in fact, I think the second paper we wrote had Abel in its title because it has something to do with locally compact abelian groups.
From what you tell us, I get the impression that your work is a good example of that the combination of motivation and insights from real-world problems on the one side and then fundamental abstract mathematical tools has shown to be extremely fruitful. And this brings me to the question whether this distinction between pure and applied mathematics that some people talk a lot about, whether that is really meaningful in your own case and maybe in general.
That distinction, I think, in my case at least, is not really there. The way I've looked at mathematics is there is a specific problem that needs to be solved. Maybe the problem is a mathematical problem, but the origin of the problem could be physics, or could be statistics, or could be another application, economic application perhaps. But somehow the model is there, and it's clear what is the mathematical problem you had to solve. But of course, if the problem came from physics or some application, there is an intuition that helps you about what the possible answer could be. And so the challenge is how to translate this intuition into rigorous mathematics. That requires tools, and sometimes the tools may not be there, and you may have to invent those tools. And that's where the challenge and the excitement of doing mathematics is, as far as I'm concerned.
May I come back to your Indian background? In fact, you are the first Abel Prize recipient with an education from a third world country. But then in 1963, you left your native India in Kolkata and went on to the Courant Institute of Mathematical Sciences in New York, where you still are working. But I wonder whether you still somehow strongly feel your Indian background in your mathematics, in your training, and maybe also in your lifestyle, your religion, your philosophy. Can you comment about that?
Well, for 21 years or 22 years, even 23 years, I grew up in India. And I think that part of your life always stays with you. So I'm still very much an Indian in the way I live. I prefer Indian food than anything else. And I have some religious feelings about Hinduism, and I'm practicing Hindu, and so my religious beliefs are based on my early life. So my lifestyle is very much Indian. Okay? But having lived in the United States, you learn to adjust a little bit, and you sort of perhaps have a combination of the two that you are comfortable with. As for my work, I think the training in India has been mainly in classical analysis, and no matter what you do, even if you do the most abstract mathematics, you use it as a tool. At crucial points, I think you need to go back to your classical roots and do some tough estimate here or there, and I think the classical training definitely helps there. And what the abstract mathematical tools help you is in sort of putting the result in some perspective, so you can see what the larger impact of what you have done is. I think to assess that, the modern training gives you some help.
The best known Indian mathematician of the past, at least here in the West, is certainly Srinivasa Varadhan. And I mean, he is well known for both his very untraditional methods and results, and his notebooks are still studied by quite a lot of mathematicians around the world by now. But he's certainly also known for his tragical fate and his untimely death. So may I ask you whether he has played a specific role in your life as a role model, and is that still true for many Indian mathematicians?
I think the name of Ramanjuan has been familiar to most Indians today. Maybe when I was growing up, it was more familiar to people from the south than from the north, because he came from the southern part of India. But we definitely knew of him, and knew of him as a great mathematician. And of course, when you're in that age, I didn't really know the details of his work, and even now I only have the vaguest idea of what it is. And I guess it's true, people still don't know how exactly he arrived at those results. He seemed to have a mental process which led him to these things which he has not fully explained in his work, and in spite of spending years with Hardy, the West is not able to penetrate that barrier to understanding how his mind worked.
You spent your life in India, the last years of your life at the ISI in Kolkata. There's another well-known Indian research institute, which is the Tata Institute. And I know that there has, at least at times, there has been a certain competition between these two institutions that are, of course, specializing on different fields. Can you comment on this competition and maybe the ongoing relations between the two institutes, their strengths, their respective strengths?
I think, I don't know where the competition started. I mean, I think the Indian Statistical Institute was started by Mahalanobis, who was the founder, and the Tata Institute was started by Baba, who was the founder. And they were both great friends of Jawaharlal Nehru, the Prime Minister at that time, so he encouraged them both. So maybe there was some rivalry at that level. That's at the institutional level. Then we come down to it, the mathematics part of the Indian Statistical Institute, the scientific director was Dr. C.R. Rao, who was my advisor. And the mathematics part of the Tata Institute was headed by Dr. Chandrasekhar, who was the moving force in the mathematical aspects of Tata Institute. Maybe there was some competition there. But I think at the level of faculty working in the two institutions, I know many of their faculty, and in fact, many of them were from the same region in the south, and they went to the same university, same college in the south, perhaps even the same high school. And so the relationship between the two faculties have always been friendly. It's true the emphasis is very different. They have concentrated on number theory and algebraic geometry and certain parts of abstract mathematics. The Indian Statistical Institute, on the other hand, has concentrated more on probability and statistics. Although there have been some overlap, it's really not that much.
We have heard that you still entertain close relations to Chennai, to India, and to Chennai in particular, and in particular to the Mathematical Institute, and you are in general interested in the academic development of third world countries, in particular through the Third World Academy of Sciences. Can you tell us a bit about your connections and your activities there?
Whenever I go to Chennai, which is not maybe once a year now, but earlier it used to be twice a year. My parents were alive. And I used to go and spend a month or two in Chennai, and at that time I have always made it a point to visit. There are two institutions in Chennai. There is the Chennai Mathematics Institute, and there is also the Institute of Mathematical Sciences, which is in Chennai. So I visited both of them at different times. You know, in the earlier times, I visited the Bangalore Center of the Tata Institute. Tata Institute in Bombay has an applied math center in Bangalore. I spent some time visiting them, and I have had students from there come to Courant Institute to get their degree and so on. So to the extent possible, I try to go and keep in touch.
You have given deep and seminal contributions to the area of mathematics called probability theory. What attracted you to probability theory in the first place?
When I joined my undergraduate in statistics, probability was part of statistics. So you had to learn some probability. And I've realized that I had some intuition for probability, in the sense that I could sort of sense what one was trying to do, and it meant more than just calculating some number, right? I mean, so I can't explain it. I just had some feeling for it, you know. I could. So that helped a lot. That motivated me to go deeper into it.
You have given deep and seminal contributions to the area of mathematics called probability theory. What attracted you to probability theory in the first place?
Yes, I have met him. He came to India in 1962. I had just submitted my thesis, and he was one of the examiners in the thesis, but he was going to take the thesis back to Moscow, show it to some of his other students, and then write a report. So the report was not coming at that time, but he spent a month in India, and some of us graduate students spent most of our time with him, traveling with him all over India. And so there was a period when, you know, we were meeting every day. And I don't know, there was some reports about it mentioned in the Indian press recently, which were not quite accurate. But one incident that I remember very well is that I was giving a lecture on my thesis work, and Kolmogorov was in the audience, and the lecture was supposed to last for an hour. In my enthusiasm, it lasted an hour and a half. He was not protesting, but some members of the audience were getting restless. And when the lecture ended, he got up to make some comments, and people started leaving the lecture hall before he could say. And he got very angry. He threw the chalk down with great force and stomped out of the room. So my immediate reaction was, there goes my PhD degree. So a group of us students ran after him and to where he was staying, and then I apologized for spending too much time. And he said, no, in Russia our seminars last 3 hours. I'm not angry at you, but those people in the audience, when Kolmogorov gets up to speak, they should wait and listen.
Of your many research contributions, the one that is associated with the so-called large deviations must rank as one of the most important. Can you tell us first what large deviations are and why the study of these is so important? What are the applications?
The subject of large deviations goes back to the early 30s. It in fact started in Scandinavia by actuaries working for the insurance industry. I think his name was Esscher, who started that subject. And he was interested in having too many claims against the insurance company. And he was worried about the total claim amount exceeding the reserve fund set aside for paying these claims. And he wanted to calculate the probability of this. In those days, the model was that each individual claim is a random variable. You can assume some distribution for it. And then the total claim is the sum of a large number of random variables. So what you're really interested in, the probability that the sum of a large number of random variables exceeds a certain amount. So you are interested in estimating the tail probabilities of sums of independent random variables. People knew the central limit theorem at that time. So the central limit theorem tells you what the tail of a sums of independent random variables is. It's a Gaussian approximation. You do the Gaussian approximation, the answer you get is not correct. It's not correct in the sense that the Gaussian approximation is still valid, but the error is measured in terms of difference. So both these numbers are very small, therefore the difference between them is small, so the central limit theorem is valid. But you are interested in how long it is, so you're interested in the ratio of these two things, not just the difference of these two small numbers. So the idea is, how do you shift your focus so that you can look at the ratio rather than just the difference? And so Esscher came up with this idea of what's called Esscher tilt, where you change your measure. It's a little technical, so I don't want to go into the details of it. It's a way of changing the measure that you use in a very special manner. And from this point of view, what was originally a tail event now becomes a central event. And so you can estimate it much more accurately, and then go from this estimate to what you want, usually by a factor which is much more manageable. And so this way of estimation was very successful in calculating the exact asymptotics of these tail probabilities. So that's the origin of large deviations. So what you're really interested in is estimating the probabilities of certain events. Doesn't matter how they occur, but they arise in some way, and these are events with very small probability, but you would like to have some idea of how small it is. So you'd like to measure it in logarithmic scale, in some sense. Is it e to the minus how big? So that's the sense in which it's used. It's formulated these days.
And these have applications also in finance, I gather. A lot of applications, this thing, is that correct?
I think in finance, one of the things, what the theory actually tells you is not so much as what the probability is, but it also tells you if an event with such a small probability occurred, how did it occur? Can you trace back the history of it and explain how it occurred and what else would have occurred? So you can sort of analyze the entire circumstance. Because, see, Esscher's method, there was a tilt that produced it. Then that tilt could have produced other things too. And they would all happen too if this event happened. So it sort of gives you more information than just how small the probability is. And this has become useful in mathematical finance because you write an option which is really, if something happens at a certain time, then you promise to pay somebody something. But what you pay may depend on not just on what happened at that time, may depend on the history. So you'd like to know if something happened at this time, what was the history that produced it? And the large deviation theory is able to explain this.
Together with Donsker, you reduced the general LDP, large deviation principle, to a powerful variational principle. Specifically, you introduced the so-called Donsker-Varadhan rate function and studied its behavior. Could you elaborate how you proceeded and what type of rate functions you could handle and analyze?
See, if you go back to the Escher-Kremer theory of large deviations for sums of random variables, that requires the calculation of the moment generating function. And because they have independent random variables, the moment generating function are products of each one. They're all the same, you just get the nth power of the moment generating function. And what really controls the large deviation is the log of the moment generating function. So the log of the nth power is basically the original log. So essentially the log of the moment generating function controls your large deviation rates. But on the other hand, if your random variables are not independent but dependent, say like in a Markov chain or something like that, then it's no longer just the moment generating function, but it's more how the moment generating function of the sum, how does it grow? It doesn't grow like a product, but it grows in some way. And this is related by Feynman-Kautz formula to the principal eigenvalue of the generator of the Markov process involved. So there is a connection between the rate function and the so-called principal eigenvalue. And this is what our theory used considerably. So the rate function is constructed as the Legendre transform or the convex conjugate of the log of the principal eigenvalue.
Before we leave this subject of large deviation principle, could you comment on the so-called Varadhan integral lemma, which is used extensively in quantum field theory, statistical mechanics, market finance, electrical engineering, and more? Why is that?
I don't think Varadhan's lemma is used that much. Maybe large deviation theory is used that much. I think Varadhan's lemma is the reason I call it a lemma is I didn't want to call it a theorem. It's relatively very simple thing. It just tells you that if probabilities behave in a certain way, then certain integrals behave in a certain way, and the proof just requires approximating the integral by a sum and just doing the most elementary estimate. So I think what is important there is just a point of view and not so much the actual estimates, and the work involved is quite minimal.
But it pops up apparently also in quantum field theory. Is that correct, or?
I think what it is it's basically the basic idea in this is very simple, that if you take two positive numbers A and B and raise it to a very high power, and you look at the sum is just like the larger of the two. The smaller one pales into significance compared to the larger one. So you can replace the log of the sum by just the max. Log of the sum of the exponential behaves just like the maximum. So that's the idea when you have just a finite number of exponentials. Some sense integrating is no different from summation if you have right estimates, and so that was how I looked at it. And I think this arises in many different contexts, so one can use the idea in many different places, but the idea itself is not very complicated.
Well, that's often with some of the most important results in mathematics. I mean, they go back to a very simple idea, but to come up with the idea, that's of course the trick. I want to ask you a different question. You realized that Mark Katz's old formula for the first eigenvalue of the Schrodinger operator that could be interpreted in terms of large deviations of a certain Brownian motion. Could you tell us how you came to this realization?
I think it was 1973. I had just come back from India after a sabbatical, and then I was in Donsker's office. We always spent a lot of time talking about various problems. So he mentioned that if you look at the largest eigenvalue, which is the asymptotic behavior of a Katz's integral, I think people know at that time that if you take the log of the expectation of a Katz's exponential, of a Katz's type function, that's asymptotically like the largest, the first eigenvalue. And the first eigenvalue is given by a variational formula. That's classical, really. It's a variational formula. And we knew that if you do large deviation and calculate asymptotic integrals, you get a variational formula too. So he wanted to know if the two variational formula have anything to do with each other. Is there a large deviation interpretation for this variational formula? And so I was visiting Duke University, I remember that sometime later that fall, and I was waiting in the library at Duke University for my talk, which was to start in another half an hour or so. Then it suddenly occurred to me what the solution to this problem was. It's very simple. See, in the Rayleigh's variational formula, there are two objects that come up. One is the integral of the potential against the square of a function. And the other one is the Dirichlet form of the function. So if you replace the square of the function and call it a new function, then the Dirichlet form becomes the Dirichlet form of the square root of the function. It's as simple as that. And then the large deviation rate function is nothing but the Dirichlet form of the square root of the density. And once you interpreted that, then it's clear what the formula is. And once you know what the formula is, it's not that difficult to prove it.
Well, this brings me naturally to the next question. If you have occasionally had sudden flash of insights, you just described one right now, when you in an instant saw the solution to a problem that you had worked for struggled with. When these flashes comes, are they dependent upon hard and sustained preparatory thinking about the problem in question?
Yes, they do. Because what happens is, once you have a problem you want to solve, you have some idea how it can be solved, and then you try to work it out. And if you can solve it the way you thought it's worked it out, it's done. It's not interesting. You know, I mean, okay, so you've done it. It doesn't give you the thrill of having done something. On the other hand, it's a problem. You do, everything falls in place except one thing you can't do. If only you could do that thing, then you'll have the whole building. But this foundation is missing. So you struggle and struggle with it, sometimes for months, sometimes for years, sometimes for a lifetime. and eventually, suddenly one day you see how to fit that small piece. And then the whole structure is complete, because that was the missing piece. And then that's a real revelation and a huge joy and satisfaction which you cannot describe.
How long does this euphoria last when you have this experience?
Well, it lasts until you write it up, you know, and submit it for publication, and then go to the next problem.
Your cooperation with Daniel Strook on the theory of diffusions led to a series of landmark papers. The semigroup approached by Kolmogorov and Feller had serious restrictions, and Paul Levy suggested that diffusion processes should be represented as a stochastic differential equation. And of course, Ito should also be mentioned in this connection. How did you and Strook manage to phrase this problem in terms of a martingale problem?
Before that, let me step back a little bit. Markaz used to be at Rockefeller University, and between New York University and Rockefeller University we used to have a joint seminar. We would meet 1 week here and 1 week there, alternate back and forth. So I remember once going to Rockefeller University for a seminar and then coming back in a taxi back to NYU, and somebody mentioned a result of Czeselski, who was a Polish probabilist who was visiting Markaz at that time. And what this result was, you can look at the fundamental solution of heat equation for whole space and look at the fundamental solution with Dirichlet boundary data in a region. Of course, the fundamental solution for the Dirichlet boundary data is smaller by maximum principle than the other one. You look at the two ratios, the ratio of the two fundamental solutions is always less than or equal to 1. So the question is, as t goes to 0, as the time variable in the fundamental solution goes to 0, when does this ratio go to 1 for all points x and y in the region? The answer turns out to be that if only if the region is convex. Of course, there are some technical aspects of sets of capacity 0 and so on, so forget about it. Intuitively, the reason it's happening is that a Brownian path, if it goes from x to y in time t, as time t goes to 0, it would have to go in a straight line, because its expectation remains the same. It's a tied-down Brownian bridge, so its expectation is always linear line connecting the two. and the variance goes to 0 if you don't give it much time. So that means it follows a straight line. That suggests that if your space were not flat but curved, then it should probably go along the geodesic. So one would expect, therefore, that the fundamental solution of the heat equation with variable coefficients should look like e to the minus the square of the geodesic distance divided by 2t, just like the heat equation does with Euclidean distance. So this occurred to me on the taxi ride back. And so that became the paper on the behavior of the fundamental solution for small time. And in fact, that was the paper that I think the PDE people at Courant liked and gave me a job. Because at that time I was still a postdoc, and I think anyway, so at that point, the actual proof of it used only certain martingale properties of this process. Didn't really use so much PDE. It just used certain martingales. And then Strook was a graduate student at Rockefeller University at that time. We used to talk a lot, and then I remember that spring before he finished, we would discuss it, and we thought, you know, if it is true that we could prove this by just from the martingale properties, then those martingale properties perhaps are enough to define it. And then we looked at it, we thought that, okay, can you define all diffusion process by just martingale properties? And after looking at it a little bit, it looked like it unified. You know, PDE, Kolmogorov and Feller through the PDE have one point of view, and then stochastic differential people have another point of view. Semi-group theory has another point of view, but somehow the martingale thing seems to unify all of it, and so it's clear that it's much more useful. And it turned out, after investigation, that the martingale formulation is sort of the weakest formulation one can have. That's why everything implies it. And being the weakest formulation, it would be the hardest to prove uniqueness for. Okay. So it became clear that the hardest thing would be to prove uniqueness. Okay. And then we were able to show that whenever any of the other methods work, you could prove uniqueness for this. And we want to extend it and prove uniqueness for a class which had not been done before. And that eluded us for nearly a year and a half until one day the idea came that we saw how to do it, and then everything fell into place.
So that was another flash of
That's
insight?
another flash.
Must have been very, very exciting.
You know, that meant that we could do a lot of things for the next 4 or 5 years. It kept us busy.
Before we leave your mathematical research, I'd like to ask you about your contribution to the theory of hydrodynamical limits, that is, describing macroscopic behavior of very large systems of interacting particles. Your work in this area has been described as viewing the environment from the traveling particle. Could you describe what this means?
Okay. Let me try to explain it. The subject of hydrodynamic scaling, as it's called, or hydrodynamic limits, has been a subject that's not really started in probability. It starts from classical mechanics, Hamiltonian equations, and it's a problem of deriving fluid flow Euler equations directly as a consequence of Hamiltonian motion. After all, you can think of a fluid as individual particles, and the particles interact ignoring quantum effects according to Newtonian rules, and you should be able to describe how every particle should move. All you have to do is solve this 10 to the 68 dimensional ODE and you're in good shape. Instead, we do replace this huge system of ODEs by PDEs, a small system of nonlinear PDEs. And these nonlinear PDEs describe the motion of conserved quantities. If there are no conserved quantities, then things reach equilibrium very fast and nothing really moves. But if there are conserved quantities, then they change very slowly locally. And so you have to speed up time to a different scale, and then you can observe change of these things. So mass is conserved, and that means density is one of the variables. Momenta are conserved, so fluid velocity is one of the variables. Energy is conserved, so temperature becomes one of the variables. So for these conserved quantities, you have equations, and these are partial differential equations. When you solve them and you get a solution, they're supposed to describe the macroscopic properties of particles in that location. And given these parameters, there is a unique equilibrium for these fixed values of the parameters, which are the average values. In Hamiltonian scheme, that would be a fixed surface with prescribed energy, momenta, and so on, so that on that set the motion is supposed to be ergodic, so that there is a single invariant measure. And this invariant measure describes how locally the particles are agitating all the time. And that is only described in statistical terms. You can't really pin down which particle is where. Even if you could, you don't really care. That's the point of view. And this program, although in a physical sense it seems reasonable, in a mathematical sense has not been carried out. And the closest thing that one has come is the work of Oscar Lanford, who has shown that for a very small time scale, you can start from the Hamiltonian system and derive the Boltzmann equations. And then you have to go from Boltzmann to Euler. That requires certain parameters to be large and so on. It's not clear in that range the earlier part of the results work. So it's the mathematical level of these things is not what things should be. On the other hand, if you put a little noise in your system, so that you look at not a deterministic Hamiltonian set of equations, but stochastic differential equations, or maybe particles that move and jump randomly, so you add a little noise, then life is much easier. Because the problem is the ergodic theory. The ergodic theory of dynamical systems is very hard, but the ergodic theory of Markov processes is a lot easier. So with a little bit of noise, it's much easier to keep these things in equilibrium. Okay, and then you can go through this program and actually prove mathematical results. Okay, and so I think the history of it is we were at a conference in Marseille at Lumini, which is the Oberwolfach of the French Mathematical Society. And my colleague George Papanikolaou, I think should be here later today. We were taking a walk down to the Calanque from, and on the way back he was describing this problem. He was interested in interacting particles, Brownian motions interacting with some potential, and he wanted to prove this result. I thought the result should be easy, it seemed natural somehow. So when I came back and looked at it, I got stuck. I couldn't do anything. And much as I tried, there were two critical steps I figured needed to be done. one step I could do, this second step I could not do for this model, so I just left it at that. Then a year later, we had a visitor to the Courant Institute, Josef Fritz from Hungary, and he gave a talk on hydrodynamic limits, and he had a slightly different model, and with by using different techniques, he could prove the theorem for that model. And then I realized that the second step, which I was stuck in the original model, in this model I could do very easily. So we wrote a paper with George Papanikolaou and one of his students, Go. That was my first paper on hydrodynamic limits. And there's more for a field rather than for actual particles. Okay. So that's what got me interested in the subject. And then when you look at particles, you can ask two different questions. You can ask, what's happening to the whole system of particles? You don't identify them. You just think of it as a cloud of particles. Then when you look at it, then you can develop how the density of particles change over time. But this doesn't tell you which particle moved where, right? Suppose if you imagine particles have two different colors, it can't give you how this, now you have two different densities, one for each color. You have the equation of motion for the sum of the two densities, but you don't have an equation of motion for each one separately, because to do each one separately, you would have to tag the particles and keep track of them. So it becomes important to keep track of the motion of a single particle in the sea of particles. And the way to analyze it that I found useful was make the particle that you want to tag the center of the universe. So you change your coordinates, keep along with that particle. Then this particle doesn't move at all. It stays where it is. And the entire universe revolves around it. So you have a Markov process in the space of universes. This is, of course, an infinite dimensional Markov process. But if you can analyze this and prove a ergodic theory for it, then you can translate it back and see how the tagged particle would move. Because in some sense, how much the universe moves around it, or it moves around the universe, is relativistic in some sense. So I found this method to be very useful, and that's how they looked at the view of the moving particle.
I see. That's very interesting. That's very interesting. I will finish now by asking you, well, first, can you describe your work style? Do you think in geometric pictures or more in formulas? Or is there an analytic way of thinking?
I like to think physically in some sense. You know, I like to build my intuition as a physicist would in some sense, of things doing things, what is really happening, understanding the mechanism which produces it. And then I tend to translate it into analysis. I don't like to think formally of starting with an equation and manipulating it and see what happens analytically. That's the way I like to work. So I let my intuition guide me to the type of analysis that needs to be done.
Your work in mathematics has been described by a fellow mathematician of yours as like a Bach fugue, precise yet beautiful. Can you describe the feeling of beauty and aesthetics that you experience when you do mathematics?
For me, you know, the attraction in mathematics is that it often has a simple explanation for many complex behavior, whether it's a physical system or some other mathematical phenomena. The underlying reason why things happen are usually quite simple. And it's finding this simple explanation of complex behavior that appeals to me most in mathematics. That's what I find beautiful in mathematics.
Getting to the last round of questions, I would like to ask about the special role that the Courant Institute of Mathematical Sciences certainly has played. You are already the second Abel laureate working at the Courant Institute, and at least in the world of more applied mathematics, the Courant Institute seems to play a very special role. Could you explain how this worked out and what makes the Courant Institute to being such a special place?
I think you go back to 1930s when the Courant Institute was started. There was no applied mathematics in the United States. Richard Courant came and he started this Mathematics Institute with the emphasis on applied mathematics. And his view of applied mathematics was broad enough that it included pure mathematics. I mean, he didn't see the distinction between pure and applied mathematics. You needed to apply mathematics and you developed the tools needed to do it. And from that point of view, I think analysis played an important role. And so Courant Institute has always been very strong in applied mathematics and analysis. And in the 1960s, there was a grant from the Sloan Foundation, I think, to develop probability and statistics at the Courant Institute, and they started it. And probability was successful, I think. Somehow statistics didn't quite work out. So we still don't have really much statistics at Courant Institute. But we have a lot of probability, analysis, and applied mathematics. And in these areas we are very strong. Of late we have added some differential geometries, so on. So the faculty of Courant Institute has always been among the best they could hire. And the emphasis has always been on analysis and applied math. And perhaps that reflects why we have had 2 Abel Prize winners out of the first 5.
That's very impressive anyway. I would like to switch to the public awareness of mathematics in general. There is an apparent paradox there at the same time where, as we could partially see from your descriptions, mathematics is somehow everywhere in our life, in technical gadgets, in description of the mathematics, of the finance markets and so many other places. Well, this is not very visible for the public, and it seems to be quite difficult for the mathematical community to put through its own importance to the man on the street and to the politician. That's one aspect. The other aspect is that it is not that easy in our times to get a sufficient enrollment of new students, of new blood in mathematics, in particular for graduate students. So I know, for example, that in the United States, more than half of the PhD students come from overseas. So do you have any ideas what the mathematical community could do to enhance its image in the public, and also how we could enroll more students into this interesting and beautiful subject? A tough question, I admit.
It's a tough question. I think people are still struggling to find the answers. But I don't think it can be done by one group alone. I think for whatever reason, probably because of the nature of their work, most mathematicians are very introvert by nature. And in order to convince the public and so on, you need a kind of personality that goes out and preaches. And most research mathematicians would take it as an imposition on their time to do research. It's very difficult to be successful in both, although there are few. Okay. So the question then becomes, how do you educate politicians and other powers that be who can do something about it, about the importance of education. I think that happened once before, I think, when the Russians sent the Sputnik in the 60s, 50s rather. That happened. I don't know what it will take now to convince. But I think it's possible to make an effort and convince people that mathematics is important to society. And I think the signs are there, because one of the powerful forces in society today are the financial interests. And the financial interests are beginning to realize that mathematics is important for them. So there may be pressure from their side to improve mathematics education and the general level of mathematics in the country. And that might in the long run prove beneficial. At least we hope so.
Yeah. Norway has made a special effort in attributing this Abel Prize, and it's not only the prize that will be awarded to you tomorrow, but there are also other competitions like the Abel, and you have been presenting prizes this morning, this one, and the prize to a mathematics teacher, the Holmboe Prize, and then there is also the Ramanjuan Prize for a prominent third world mathematician. How do you judge these activities?
I think these are very useful. I think they raise the awareness of the public, and hopefully all of this together will have a very beneficial effect in the not too distant future. I think it's wonderful what Norway is doing.
In my very last question, I would like to leave mathematics behind and ask you about other aspects of life and your interests and the things that you are particularly fond of. What would that be?
I like to travel. I like the pleasure and experience of visiting new places, seeing new things and having new experiences. Always enjoyed travel. And in our profession, you get the opportunity to travel, so I've always taken advantage of it. I like music, both classical Indian and a little bit of classical Western music. I like to go to concerts if I have time. I like the theater. I like New York is a wonderful place for theater. And I like to go to movies. And I like reading Tamil literature, which I enjoy. Not many people in the world are familiar with Tamil as a language. It's a language which is 2,000 years old, almost as old as Sanskrit. It's perhaps the only language which today is not very different from the way it was 2,000 years ago. So I can take a book written actually poetry written 2,000 years ago, still be able to read it. So that, to the extent I can, I do that.
Well then, at the end I would like to thank you very, very much for this interesting interview. And these thanks come also on behalf of the Norwegian Mathematical Society, the Danish Mathematical Society that I represent, and the European Mathematical Society. Thank you very much.
Thank you very much. I've enjoyed the experience too. Thank you.
Thank you.